Thank you so much, Paul. Good afternoon, East Coast folks, and good morning for the West Coast. My name is Burak Çeşme. I'm at Kittleson in our Boston office, and I'll be presenting some of the key findings from the third case study, which is from Colorado C470 corridor. And because Mohammed and Paul already did a pretty good job explaining the steps, I'm going to speed up a little bit just so hopefully, participants will have some time to ask questions at the end. So again, as I mentioned, our third study was from Colorado, the C470 corridor, which we looked into a freeway with several interchanges. And we worked pretty closely with Colorado DOT, especially when we were obtaining data on the corridor. So there were a few reasons for selecting this corridor as part of one of our case studies. First, the corridor had relatively good data, and I'm intentionally saying relatively because, as Paul mentioned, maybe we were not as much data rich in terms of some of the data, but still it was good enough for us to be able to test the 2019 methods. Additionally, the corridor experienced diverse travel conditions, not just peak hour recurring congestion, but also weather-related congestion due to crashes and etc. And lastly, we conducted the analysis using a different microsimulation software tool that was used that was different from the first two case studies. Next slide, please. So in terms of the planning, step one, planning and scoping, the objective of the study was to develop alternatives that can reduce congestion, that can improve operational performance and address future transportation needs. For the proof of concept demonstration, we selected key performance measures, including corridor travel times and continuous count station flows that was available to us. Just in terms of a little bit of the context, the corridor was roughly 15 miles. We focused on the morning peak, just because we recognize that there were those diverse conditions that I mentioned earlier in the morning peak, and we thought it was sufficient to serve as a proof of concepts. And the corridor included 9 key interchanges and 13 ramp termini with signalized intersections. Next slide, please. So step 2, which was the data collection and analysis, we did collect, similar to other case study teams, various type of data. Obviously, things like geometry data to be able to develop the model, signal timing data, incident data. We were able to get from Colorado DOT. We had weather stations that are relatively close by that we were able to get the weather data. We also, similar to what other teams did, were able to obtain travel time data from probe vehicles as well as continuous count station data. Next slide, please. So after data collection and data cleaning, we basically prepared our data to be able to use as an input for the cluster analysis and applied the elbow methods in k-means clustering. So based on the results of the cluster analysis, even though it's not exactly very clear, you can kind of see the elbow shape that's happening around 5. And we also did, similar to what Paul mentioned, additional analysis looking into different types of clusters and also creating those visualizations that Mohammed mentioned as well to be able to sort of figure out if that's elbow shape occurring at 5 generally makes sense. And we ended up selecting 5 clusters for this case study as well. Similar to the Florida DOT case study, we thought visualizations related to travel characteristics are important and they can help understand system performance. And that's what you see on the right side of the slides, which is basically the fundamental diagram. You can see the speed on the vertical axis and the flow on the horizontal axis in vehicle per hour per lane, and the 5 clusters that we were able to come up with. A couple of things that I just want to highlight real quick here. Hopefully you can visually see that the low demand cluster, which is shown in gray on the top left of the figure, as you can expect, it's the low demand cluster. It's happening in the free flow regime in the fundamental diagram. Then when we move on to the more congested regimes, you can see first the low congestion scenario, which is shown in orange. And I guess when we say low congestion, please keep in mind, these are not free flow. There's a little bit of congestion, but it's not resulting in breakdowns. And then we have the recurring congestion, which is shown in blue. And finally, after the breakdown happens, you can see the purple one, cluster number 4, which is the crash-related congestion. And probably the most important thing from the methods perspective was If you look at, if someone simply models the recurring congestion, which is shown in cluster 0 blue, that roughly corresponds to 35% of the entire year. So therefore, it's important, again, to be able to capture these different travel conditions, and that's where the strength of this cluster analysis comes from. Next slide, please. Again, the step 5 for model calibration, the first sort of item that we did, similar to other teams, was the identification of the representative day for each cluster. And consistent with the 2019 methodology, we selected the representative day based on the minimum deviation from centroid for the key performance measures. Keep in mind, this is not a synthetic date, this is an actual date, as other team members discussed. And the table that you see here is showing the selected representative days for those clusters and also displaying their travel characteristics. So just a couple interesting observations here that I want to capture. So if you look at cluster number 2, low demand cluster, that's happening on July 4th. That makes sense, especially keep in mind we focused on the AM peak, 6 a.m. to 9 a.m., not PM peak. So again, you would expect pretty low volumes on July 4th as well. A couple other interesting observations. If you look into cluster number 3, weather influence cluster, you can see the visibility is only 0.7 miles, much lower than other clusters. Again, that validates the cluster with respect to the representative day. And similarly, crash influence cluster has the highest severity index, which was something we developed that sort of represents the presence of a crash as well as how severe the crash is. Next slide. So I'm going to relatively go fast with these. We went through the same exercise in terms of model calibration, where for each cluster, we developed the sigma bands using the 1 sigma band and 2 sigma bands or the variation envelopes. And the example that you see here is just from one of the clusters, which is recurrent congestion, but essentially we created these variation envelopes for each cluster that was identified. Next slide. So once sort of we identified our clusters and created the variation envelopes, we start to look into these different criteria that other team members discussed. Again, I'm not going to go into the details, but just a little bit of how we calibrated the models. Generally speaking, we didn't make changes to driving behavior and car following for a lot of the clusters, except for the weather-related cluster. And when we looked into the actual data with weather-related cluster, we recognized that the free flow speeds on the corridor was much lower than the free flow speeds on, let's say, low demand cluster. So that was one change we did based on field data. We also made some headway adjustments in terms of car following behavior using some of the suggestions that was provided in highway capacity manual. Next slide, please. Next slide, please. Thank you. So the last step was alternatives analysis. So for the Colorado DOT case study, we basically tested both geometric improvements as well as operational improvements. So for the operational improvements, we established what we call as local ramp metering, pretty simple fixed metering rate type of ramp metering on some of our on-ramps, but also for 2 of the on-ramps that had relatively high on-ramp demand as well as relatively low acceleration lane, we made, at least hypothetically in this proof of concept demonstration, we extended those acceleration lanes as you can see on the slide. Next slide, please. We also went through the number of replications and selected the minimum number of runs, which was 9. That came from the recurrent congestion and something we applied for when we were conducting the alternatives analysis. Next slide, please. And in the last step of our alternatives analysis, we performed hypothesis testing as well to compare the results obtained from the alternatives and to determine basically if the difference in performance measures are statistically significant. I think the results that you see on the table below are really important, again, highlighting some of the strengths of the 2019 methods, especially from a decision-making perspective, because if you look, you can see that alternative 1 in this case, which is what we are testing compared to a baseline scenario, if you will, the ramp metering and extended acceleration lanes, they were able to reduce the freeway mainline delay by about 9% approximately, right? But when we perform the statistical testing, the results showed us that it was not, we basically, we couldn't accept the results, or I guess the null hypothesis cannot be rejected because the differences in terms of the benefits were not as high, and the standard deviation of some of those scenarios were relatively large. That led to the conclusion or the outcome that the null hypothesis cannot be rejected. So that's pretty much it from the Colorado case study. With that, I would like to turn it over back to David.